Okay. So, in the last class we discussed in 3D hydrodynamic turbulence what is the spectrum and flux, right, but that was for the inertial range, right. So, when the nonlinearity is very strong compared to viscous term is finite but non-zero, then and Reynolds number. So, I did define Reynolds number, no. Yes. So, Reynolds number is large, then we get a turbulent cascade, scale by scale transfer, and that cascade leads to k to the power minus 5/3 spectrum. The question is, so this is what I summarize in my next slide. So, the spectrum is k to the power minus 5/3 and this is the flux. So, if you plot this function of wave number, y axis is flux. So, flux is constant and flux decreases. Well, I should not have said, this is the topic of today's lecture. So, this where flux is constant and this flux equals the dissipation rate, that also I proved, right. So, if you from that equation for the flux you take this equation k naught as wave number k naught and compute flux energy in given by the external force matching the dissipation, you can match the two under steady state. So, flux pi u k is approximately, there is slight change as I said is epsilon u, epsilon is slightly bigger than pi u, right, I discussed in the class, or slightly different, that depends, okay, but they are approximately equal. Now, this for the inertial range. So, viscous term is strong here. So, in this region the spectrum is minus 5/3 and flux is constant. Now, question is what is the flux or spectrum in this band for. So, we in my book I make the notation k di, di is dissipation is starting, it is not there yet, but is starting, and the thing which I said k nu, or sometimes I was writing as k d, Kolmogorov wave number is not this, okay. Kolmogorov wave number is somewhere here, k nu, okay. So, k di is where this 5/3 spectrum is not valid anymore and is getting into some different form. In fact, we want to study what is the spectrum in this region, spectrum and flux. Is that clear? This is inertial range and this is a dissipation range d, full region, this one. So, that is the topic. Now, it is true in standard textbooks you will find that they do not talk about flux in that range, or inertial spectrum is argued, but not so much in standard books. In fact, there are many people may say that flux is 0, your nonlinearity is weak. It turns out as long as there is nonlinearity there is a energy transfer, because so if there is a nonlinearity there is u dot rad u, energy equation will have u dot rad u dot u, right. So, there is a nonlinear interaction k equal to p plus q. So, flux will be non-zero. So, even for laminar flows where Reynolds number is not equal to 0, but order 1, there too there is a flux. It is a misunderstanding that flux is 0 for laminar flows. As long as there is nonlinearity there is a flux. So, flux does not require the flow to be turbulent. Flux is constant for turbulent flow, turbulent hydrodynamic flows, that I proved it, no. So, please remember the how do you show that flux is constant is d pi by dk is 0, because this side was force minus dissipation. Now, we say that in the inertial range force is 0 and dissipation is weak. So, this was approximately 0, but we say well we ignore it. So, flux is constant pi u, but in real flows of dissipation is not 0 in laminar flow. So, the flux will change, okay. So, that is a, so this equation is for me is very powerful equation, and that tells you about flux, okay. So, let us see. So, we will work with first when Reynolds number is much larger than 1. So, this theory is for large Reynolds number, and I will discuss only Pauw's model. There are one more, there is one more, but I will not discuss all models. Okay. So, this course, so we will discuss selected model which is kind of fits with the data better. So, this model by Pao, which is very old model, 1960s. So, this is for both inertial and dissipation. This formula will work for initial as well as dissipation approximately. Okay. It is not fully true, it is only approximately valid. We know there are deviations from Pau's model in simulations. So, we start with the same equation. Huh? So, inertial range, my force is 0. So, d pi by the flux will change with k, and how will flux change? Because of dissipation, right? Everybody is happy with this. So, this is one of the most important equations. Okay. D pi by dk is minus 2 nu k squared uk. Now, so this is what we want to use. Unfortunately, there are two unknowns, right? Pi u is also unknown and u is unknown, and I have only one equation. So, you can't solve this. So, Pao suggested that let us make a model where we assume that EU by pi u, this one, this ratio. So, I need one more equation. According to him, let us try to make EU by pi u independent of viscosity, nu and forcing. So, he makes an assumption. So, well, let us assume that this only depends on the flux and wave number. Flux means pi epsilon u, okay, flux epsilon u are same. Okay. So, this is what, let us assume it, and if that is the case, if you must make this assumption, then dimensional analysis will tell you that it must be this. Okay. So, u by pi u has some dimension, this is L cube by t squared and this is L square by t cube. So, if you match the right hand side, you will get this. In fact, I am just following the Kolmogorov theory. So, Kolmogorov theory says u is k Kolmogorov epsilon u to the 2/3 k minus 5/3, divide that by epsilon u, you get epsilon u minus 1/3. So, I am also putting the constant. Okay. So, in fact, Pao put the constant. This is Pao's model, not my model. Okay. So, so we have now two equations and two unknowns. Now, it is easy to solve, right? It turns out it is very trivial after this. So, once I substitute EU from this equation, so I just replace U by pi u multiplied by this. So, you will get this. So, this is a ODE is function is of pi u is a unknown variable. Okay. So, here I had put epsilon u by intention. So, the right hand side is only function of k in this part, a k and epsilon u. Epsilon u is a constant. Okay. So, this is so what is the form of, so forget about all the constants, how will pi u look like a function of k? So, what is the solution? Is a linear first order equation. So, d pi by dk, please tell me what is the function? What is the form of function? K to 4 by 3 and exponential. Okay. So, d pi by pi is this integral. So, it will give you log in the left hand side and the right hand side is k 4/3. So, exponential minus k 4/3. So, the solution is, you can immediately see apart from constant is exponential minus k 4/3. Now, remaining part is just algebra, you know. So, we need to, so please remember it can't be k 4/3, it has to divide by, so k has dimension, no. So, I can't say sine of 1 meter, it does not make sense. Have you heard of somebody saying sine of 1 meter? Sine of 1 you can say. So, sine, the argument of sine must be non-dimensional number or exponential of 1 second, it is not ever meaningful. So, you have to divide this by some quantity with dimension of k. So, it turns out we get quantity k nu, same as what we defined earlier. Okay. So, it is a Kolmogorov wave number k nu comes, which is epsilon by nu cube to the power 1/4. Okay. So, this algebra I will not do it here, you can easily do, but the form is exponential. It is not k squared, it is k 4/3, it is slightly I mean it comes from because of phi third. The origin of 4 third is coming from this phi third will multiply by k squared. So, you are remaining with k 1/3, integrate that you get 4 third. Okay. So, the solution I will just tell you, this is a full solution. So, k by k nu to the power 4 third, and in front there is a 3 by 2 k Kolmogorov, which is order 1, and pi u has dimension of epsilon u. So, epsilon u is coming here, which is nice. Okay. So, what does it mean? If I plot this function of k as pi u, so it is constant. This is also called stretched exponential. No? It is delayed exponential. So, exponential drops quickly, exponential would have dropped like this, but because of this 4 third it drops bit slowly. By the way, flux is always decreasing with k. This is telling you that flux is not constant, flux is always decreasing, but decreases rapidly after some wave number. So, k nu is somewhere here, but maybe k nu by 2 is somewhere, k nu by 2. Okay. So, in fact, it would be interesting to see, make it quantitative, at what value it has pi has become half. It is a good number to investigate. I have not done it, but it is a good thing to play around. Okay. Is that clear? So, flux always decreases because of dissipation. So, even in the inertial range, dissipation is important in real flows. So, flux is decreasing even in the inertial range, but it is less decrease, but then it rapidly decreases in the dissipation range, and this exponential part will become important in the dissipation range. So, flux is non-zero in the dissipation range as well. Okay. Now, Kolmogorov assumes viscosity going to 0 limit, and that is what he basically says, well, this k nu is at infinity. So, as a mathematician he is ignoring it. So, well, let us push it to infinity, and so Kolmogorov is essentially gets the constant. If k nu is infinity, then this exponential part is 1. So, exponential power infinity is exponential power 0, sorry, exponential power 0 is 1. Okay. So, that is why he gets. Now, whatever the spectrum can also be solved. So, power told you, what does power tell you? E by pi is epsilon minus 1/3 k minus 5/3. Okay. So, I know the pi now. So, I can just take it to the right hand side. So, you will basically at Kolmogorov multiplied by stretch exponential. So, the formula for a spectrum is this Kolmogorov part, and I multiply by the exponential part, stretched exponential. Okay. So, this is the prediction of power. Now, k nu I told you is this, which is Kolmogorov wave number. So, this has a name, so please remember Kolmogorov wave number. Now, let us see whether this fits with the simulation, high resolution simulation. Okay. So, there are many plots. So, let us try to understand. So, this is done by us. So, this paper which is to be published, Verma et al. So, there are many people. So, these are for different resolutions. So, 512 cube, 1000 cube and 4000 cube. So, let us look at, and the 3 curves. So, red is the DNS from simulation. DNS is direct numerical simulation. Okay. We do not make any assumption on viscosity or some model. Periodic box 2 pi cube, like what I described. So, red is the simulation. Now, POW is the green curve. Okay. And the left and the Pope model, which I am not describing here, is also a model which is a dash curve, dash black. Now, this is a flux. So, we make a tilde, no. So, tilde is normalization. So, this one is pi divided by epsilon, is pi tilde, epsilon u. Okay. I am not writing this one. Okay. So, it should be 1 in the initial range, then should decrease. So, let us look at the flux first. So, flux is decreasing, the simulation is this line, but on that the data points are all circles. Okay. So, red line with circles are the simulation data. Now, green is overshooting, but somewhat okay, it fitting quite okay with the data phi 12 cube, but this black line is not fitting. So, POW is not doing good for flux, sorry, POPE is not doing good. POW is doing quite well for phi 12 cube. Here also for 1000 cube it is good. So, this drop of flux is captured by POW, but it is not doing well for 1000 cube. You see, it is slightly quite off by factor 2. Okay. But flux is decreasing. If you look at this thing, flux is decreasing even in the initial range, okay, because viscosity is taking the energy out, becomes stronger and stronger for large k, because viscous term is nu k squared E k. So, this k squared term and phi third is here. So, k squared is getting more and more important for larger k. Okay. So, this is what is happening here. So, this is increasing. So, the flux is decreasing. So, that is one thing I want to emphasize. What happens to the spectrum? Spectrum, the green line is below the red line, but somewhat fine, is almost looking quite good, except here again the green is above, but here green is below the red. Can you see the green is below the red? There is a gap. So, the red line is above green, and there is, this is called bottleneck effect. So, in crude sense, so well, this is still remains unsolved problem in some sense. People are not agreeing on one mechanism, one universal one mechanism which everybody will say, well, this is the reason for bottleneck effect. But it is like you are running on a highway, driving on a highway, but suddenly you have to go to a city, you know. So, you take basically take the detour to the, or rather you get off the highway. So, there is normally congestion at the knee, you know. So, speed is coming down. So, there is a dissipation, and as a dissipation the speed of cascade is decreasing. So, to increase the dissipation at that region, so there is jam, there are more cars at the turning point. In some sense, that is intuitive picture I can explain why bottleneck is there, because there is the amount of car which is travelling on the highway, as well as let us say you have to go to a smaller road, jammed road or dissipative road. Dissipative road, the speed has decreased. So, basically there is more cars, and that is what is kind of happening, but it needs more resolution. I mean, it needs more arguments, and so this is a bottleneck effect. Okay. So, POW's model is not fully correct. POW's model assumes that it is a mean field theory. So, there is a constant flux, and it is not taking care of subtleties of turbulence. Okay. So, we need to worry about this aspect, but it is good, no, I mean to first order is a very good model, and it seems to do well even for 2D helical turbulence. So, at least we have been quite successful in modeling lots of flows with POW's ideas. So, this is about Reynolds number much greater than 1. So, I gave only one model, but this model also is useful for the dissipation range, which we need it for many situations, like rotating turbulence, where there is a strong I mean energy is quite small in lot of range of wave numbers. This model is doing very well. Okay. So, this is what we find in recent work. Now, let us look for laminar flows. So, laminar flows is or dissipative flows. Okay. This the name is different, names are given by different people, but I just call it laminar, where Reynolds number is 1 or order 1, or it could be 10 as well. Turbulent flows requires Reynolds number to be 10 power 4, 10,000 or so, or 10,000 or bigger. But Reynolds number is when it is order 1, then nonlinear term and viscous terms are same order, no. What is Reynolds number? Is the ratio of n-lin by viscous. So, we say that viscous and n-lin terms are of the same order. So, flux constant is not true anymore, but what about the what happens to the flux? And you find in many papers they say flux is 0. You drop the, we assume the nonlinear term is negligible, including Cambridge papers. So, I can so no, don't take all the experts with a lot of faith. So, you should trust your own ideas. So, Reynolds number is order 1, that means nonlinearity is important, is as good as viscous term. So, you can't just keep viscous term and ignore nonlinear term. If you keep the nonlinear term, then there is a flux, from the argument which I was giving in the first slide. In fact, it is straightforward. So, we take the same equation, d pi by dk is minus d nu k, and this is it. Now, you may say, why not try the Pauw's model? So, I can use the same idea of Pauw, in fact same formula for Pauw, and try to fit in the numerical data. Is that k nu will be small? But it turns out, I will not show you here, that Pauw's model does not work for laminar flows. We had simulation data and we tried to fit Pauw model, it simply did not work. The lines were very, very different. I am not showing you here, but you can look at the paper which is about to come. So, idea is to look for some other formula. Now, the Pauw idea that E by pi or pi by E is independent of nu and viscosity is not, that does not work very well, but what I thought was, let us try something which is obvious function. Now, if you have something like this one, d pi by dk is EUK, let us say ignore this part, well you can't, I guess you will see this, let us drop this term. Then what do you expect, which function will satisfy this? So, here df by dx is minus g, which function will satisfy this? One function will satisfy this very easily, sine, no, sine gives you cos. So, you are in the right direction, but you should exponential. So, just put e to the power minus k for both. So, you take the derivative, get is minus k. So, exponential is a good function, pure exponential, no stretched. So, I said, well, try exponential, but this k squared will cause some some golmaal. So, this k squared will make some trouble, but that is okay, we just have to solve it properly. So, they are polynomial. So, it turns out we model EUK is, well, this algebra I will again leave it, this again fitting with the model, fitting with simulation. This was not, I can't derive this fully from the first principle, we do fit from the simulation. So, exponential is the leading factor, and it turns out if you try to fit with the data, which I have the data in the next slide, I think I have the data simulation. In the simulation, if you have divide by k, it fits with the data. Okay. So, this 1 by this k is the additional thing we fit from the simulation. Okay. Now, I really welcome some of you to try out from the first principle, try to derive. Pauw's model comes from the first principle, it does not require any one assumption, but you can derive it after that. But this one requires simulation. In fact, this prefactor is coming from simulation. And Kd bar, I did not write in the slide, is square root Reynolds number by L. This again fed from the simulation. Okay. But the idea that it should be exponential is very intuitive idea, just guesswork. Now, because of k squared, this front part is polynomial 1 plus k. Now, you can fit this and things will cancel. Now, epsilon u bar I did not write again in here, but is there in the notes, u squared by r e cube 2 nu k d square. Okay. So, epsilon u is for viscous term, it is for viscous term, what is the dissipation? By the way, it is not u cube by L, no? Is nu, it is a viscous term, nu Laplacian u. So, it is nu u squared by L squared. So, that is estimate for laminar flows. So, it is come from nu u squared, but there is some normalization which we get from simulation. Okay. So, this prefactor is coming because of k squared 1 plus k, and this model is also very good when the flow is Reynolds number is order 1, is excellent. Okay. So, there is a energy at different scales even for laminar flows. So, spectrum, again I have not seen a paper published. There is one paper came recently, one paper which came recently by Srinivasan's group, which has done the simulation other than us. So, this is normalized. So, 1 by k is there. So, k E k, and there is a prefactor, no, there is a u cube by r e squared, u squared by r e cube. Now, is there the prefactor? We also multiply the prefactor, so that you get a universal function. So, this is important. So, let me go back. So, we want this function to be compared. If this is your conjecture, then what should you try to fit with various Reynolds number? So, EU multiply this by k, divide by u squared by r e cube. What will that give you? Exponential minus k by k d bar. So, x axis should be what? Should we put k or k? What should I choose? K by k d bar. So, y axis will be just exponential of, so this non-dimensional number k prime. So, plotting is also an art, you should really know how to plot. So, x axis should be k prime, just k by k d bar, and y axis should be not EU, y axis I should plot this for different runs. So, if you plot this, then I will get one line for all of them, same line, they all collapse, this is called data collapse. Okay. And we will collapse the exponential minus k, k prime minus k prime. Okay. So, this is what we did this from, this is a guesswork, this really requires doing back and forth, guessing, and same thing you do it for here as well, the exponential part, divide by 1 plus k. So, you have to just do it. So, it is collapsing nicely, no. So, x axis is k prime, k bar, which is k by k d bar. So, we put a k d bar. K d bar is for laminar, not k d. So, k d and k d bar are different. K d is the notation, k d is same as k nu, which is Kolmogorov number. And this is flux, where we divide by 1 plus k bar as well, 1 plus k prime. So, you make the function which is universal. These are called universal function. Why universal? It is true for all data, true for all runs, as long as Reynolds number is order 1. So, our Reynolds number is here. So, viscosity is listed here, and Reynolds number is 49 to 17.6. So, this corresponds to 17.6 and this corresponds to 49. So, Reynolds number is not too small, no? So, our runs were not less than 1. So, it fits with this. So, this requires some more work, and these runs are very cheap. We can do it on 64 cube, and it is a 3D runs, and they are all steady state flows. No? So, there was forcing, wait for steady state, look at the spectrum, and that is what we get. Okay. And this seems like a good model, and laminar flows are also important, though this course is on turbulence. There are many flows which are laminar. So, like human body, within the human body, all the flows except near the heart, things are laminar. Blood flow is laminar. Okay. The fish swimming in the ocean or river, they are laminar, so they are not very fast. Or also many engineering flows, slow moving, honey, pipe, and so on. So, the earth mental is slow. So, there are many flows which are laminar. Okay. So, that is what about Reynolds number 0? Reynolds number 0 is trivial. sorry, yeah, the nonlinear term is dropped. So, for steady state d by dt also will be dropped. So, if R is 0, then if there is no forcing, then we will basically get, so there is no, well, basically steady state the forcing must match the viscous term. So, u dot plus u dot grad u is 0, so f plus nu k grad square u. So, viscous term must match the because that is what is the steady solution. So, that is what I wrote in Fourier space, that is what we will get. So, spectrum will be 1 by k4 forcing mod square, okay, this just straightforward. What if I say that, well, there is no forcing, but it is decaying? So, spectrum will be this one, here there is no flux. So, there is no d pi by dk, okay. So, flux is 0 for R is 0, right, there is nonlinearity, nonlinearity is 0, so there can't be any triad, no flux. So, spectrum will be exponential, it is a diffusion equation. So, diffusion equation, each term, each wave number energy will drop as Gaussian, e to the minus k square t, it is a diffusion equation. So, finally, everything will go to 0, but it is a diffusion equation. Okay, so stop, thank you.